Alright, so today we are come to talk about the cyclic formation of sugars. But before that, when we are talking about sugar, sugar refers to molecules that are called saccharides. For that matter, we have a monosaccharide, disaccharide, and oligosaccharide. When we are talking about monosaccharides have one sugar, okay, or one molecule. It is made up of only one monomer. When we are talking about disaccharides are made up of two sugar molecules which are linked together by a specific bond called glycosidic bond. The same way when we are talking about oligosaccharide deals with few sugar molecules that are linked together, which is about 3 to 9 or 10. But when we are talking about polysaccharides, they contain a lot of many sugar molecules that are linked together, about 10 and more. Now, as we delve into, let's talk about the cyclic formation. Let's take this sugar for instance, which is called an aldose because it contains the aldehyde functional group. And as you can all see, so this sugar, as you can see, is an aldose, okay, because it contains the functional group and aldehyde. Okay, so to begin with, we can start from the cyclic formation of this sugar. So as you can all see, before it forms a cycle or a cyclic formation of the glucose, before it begins, the sugar is already in its straight chain. Okay, as you can see, it is in its straight chain, which have represented it by the facial projection. Okay, so the place where you are seeing, the place where I have indicated the arrow, okay, this place is called an anomeric carbon. The reason why it is called anomeric carbon is that, as you can see, that carbon is not a chiral center at first. Before the cyclic formation occurs, this is not a chiral center, though it's a carbon atom. This is not sp3 carbon because it's having a double bond bonded to oxygen, and it is not bonded to 4 different atoms or groups of atoms. And that's what I'm trying to say. So this is an anomeric carbon. The reason why we are saying it's an anomeric is that later you find out that this carbon is going to become a chiral center. It's going to form a serogenic center after the formation of the cyclic sugar. That is why it is called anomeric carbon. So anomerism is simply about the formation of a chiral center after a cyclic formation of a compound is formed. Okay, so as you can all see, there are conditions that you need to consider before the hemiacetal formation occurs. Okay, there's a condition that you need to consider. The first condition that you should keep in mind is an acidic medium. This reaction or this mechanism must occur in an acidic medium. Okay, so in an acidic medium, we can take H2SO4 as an example. The second one is moderate temperature. The temperature must be moderate in order for the reaction to proceed successfully. Now let's delve into ritual, which is the cyclic formation of glucose. This is a glucose molecule. So this sugar being a glucose, there are some things you need to consider. It can be a D-glucose or an L-glucose, depending on the position of the OH group, this OH group, on the last but one carbon, okay, or the chiral carbon, the last chiral carbon, which is also called the penultimate carbon. Now, before the formation occurs or before the mechanism proceeds, as I said earlier, this occurs in an acidic medium. For that matter, this aldehyde functional group, this oxygen, usually they don't show that it has lone pairs, but it is having lone pair. Okay, so it undergoes a nucleophilic attack. So these lone pairs are the ones that are going to attack this acid. So it's going to protonate this acid. No, it will deprotonate this acid. Okay, for it to release one of its hydrogens. Now, This oxygen will be bonded to what? The new oxygen, the new hydrogen that has been what? Protonated from the H2SO4 to have something like this. So from here, just look at the mechanism very well. This one attacks the acid. The acid does not take part of the chemical reaction or the mechanism. So later you are going to find out that at the end of the day, you are going to get your H2SO4 back. So it doesn't take part in the reaction. It just occurs in an acidic medium. Now, when you're having something like this is your hydrogen, your partially negative hydrogen, and this is your partially positive oxygen. Now, let's focus here. When you are talking about hemiacetal formation, this usually occurs when the OH group, when an hydroxyl group attacks an aldehyde group. So before there's an attack, there's something called mutual rotation, where these groups, where on the fifth carbon, the groups that are bonded to it, the OH, the H2S, the H2OH, and the hydrogen, they are going to undergo a switch. They are going to undergo a switch before the cyclic formation occurs. And before they can undergo the switch, there should be a bend. So the molecule must bend. This molecule, it must bend before the cyclic formation occurs, because you can't have something straight and later get it as a circle without bending. It has to bend. So here we expect that this H2CH2OH, we expect it to come here. So if you are moving anti-clockwise, then this means that this COH, this CH2OH, it will go to this side first before it moves to this side, which is a double switch anti-clockwise, or it can go a single switch clockwise, where the CH2OH will come to this side, this hydrogen will come to this side, and this oxygen will come to this side. Because at the end of the day, there must be a rearrangement. For the electron cloud formation to occur. There must be a rearrangement where this OH will have the ability to attack the carbonyl group, which is the C double bond to the oxygen. So from here we have this structure, because at the end of the day, mutual rotation has occurred, switching the groups CH2OH, the H and the OH around the carbon 5. So from there, the molecule will bend. So when this molecule bends, this is what we are going to have. This molecule is going to bend at every carbon. So if you are drawing the Hayward projection, when we are having the OH on the right, this means that it must come to the down when you are drawing it. So the OH must come to the down. If the OH is at the left, it must go up when you are drawing the Hayward projection. So now, after the molecule has bent, you are going to get something like this. Remember that still the protonated hydrogen is still bonded to the oxygen. So now, as you are having this, you can see that if you don't do the switch, the distance between the OH group and the carbonyl group will be very high, which may not lead to the cyclic formation of the sugar. So this OH group is rather going to attack this carbonyl group. Now, depending on the position or depending on the phase at which the OH group attacks, we are going to get something like alpha glucose or beta glucose. So depending on the position, and as you can see, this group, this carbon, is having two-sided faces, one at the top, one at the down. So it's either the OH group attacks the carbon from the top or attacks the carbon from the down. That leads to the formation of either alpha or beta. So now when it attacks it, now this oxygen will move to this direction and this OH group will also attacks it. Now we have something like this. Now we don't actually know, we don't have to determine whether it is a beta or alpha, because depending on the position of the OH group, if the OH group is at the top, then we are having a beta. If the OH group is at the down, we are having an alpha. Now as I said earlier, the acid does not take part in the reaction or the mechanism. So the OH minus may be up or may be down. But let's focus on this oxygen. Okay, this protonated oxygen. Now, the HSO3 or the HSO4 plus is going to deprotonate this oxygen back to take its hydrogen. Okay, so you're having minus and you're having positive. Later, it's going to take it back. Now, when it takes it back, we have only oxygen here. So this is actually the structure of what? Structure of a glucose. Still in the acidic medium, as we are still having our A2SO4. So this is actually supposed to be 4. So H2SO4. Now, to find the product that may be formed, the product that may be formed are 2, the final product here are 2. You will be having the alpha and the beta all in the solution. This is due to the direction from which the OH group on carbon 5 attacks the carbon 1, bearing the carbonyl group or bearing the oxygen. Okay, so it can either attack it from the front or from the back. Now, if it attacks it in other ways, if it attacks it, we may have the OH being at the top, or we may have the OH being at the down. When the OH is at the down, we are having alpha glucose, and when the OH group is at the top, we are having the beta glucose. Now, there are some things that we should consider here. If you look at this structure, for instance, it's a cyclic compound. There are some factors that we should consider in order to know their stability. The OH group, which is the hydroxyl group, is a bigger molecule as compared to hydrogen. Okay, this group is bigger than what? Hydrogen. So according to the stability, if we could remember back in our studies, which is organic chemistry, we'll be able to determine whether the position of some groups of atoms on the carbon may affect its stability. So when we are having this OH group at the top and we are having this OH group at the down, they are not in the same plane. So regardless of their size, there will be no steric hindrance, or even if there will be a steric hindrance or a repulsion between this OH group and this OH group, it won't be as much as compared to the alpha glucose, where we are having the OH group at the down and the OH group also at the down. There will be an interaction, which is usually a repulsion. So there will be an interaction which will cause this to be less stable as compared to this. Okay, so after the cyclic formation of this sugar, you will be having a beta glucose and an alpha glucose all in the same solution. But there's one thing you should also note. These will be interconverting each other. We may have most of the alpha glucose converting into what? Beta glucose. The same way we may have few of them that are converting into what? Alpha glucose. That doesn't mean that all the carbons or all the sugars must have, or all the sugars that are beta configuration are stable. There are some few exceptions. For instance, mannose sugar, it rather tends to be in its alpha configuration due to some specific reasons such as hyperconjugation, okay, which I'll be explaining in my next video. So now, there is a minute of the glucose or the sugar that remain in the straight chain, okay, because it is a hemiacetal formation, or because it's a hemiacetal mechanism. There is still some form of reactivity, for that matter, as it continues to switch in between the alpha and the beta. Before it switches from alpha to beta, it must first get to the what? The straight chain before it moves to the what? To the beta. So at the end of the day, if you are having 64% stable for beta glucose, you are going to get, let's say, 35.8, where you are going to get minute of the percentage being in your straight chain. Okay, so this is all is about the formation. This is all about the formation of the sugar in their cyclic form. So when you are drawing the Hayward projection, what you have to keep in mind is that when you are having the OH group at the right, when you are drawing the Hayward projection, the OH group should be down, depending on the position. Now, I think you understand more on the formation of sugar, so I'll be explaining in my next video how the formation of sugars like cyclic sugars with 5 rings. They are called the furanos, okay, or the furan, and same as the one that I've already explained. So these 6-membered ring sugar are called pyran or pyranos, depending on how you are going to pronounce it. Now, there's a question that I want to actually discuss with you. It's all about stereochemistry, but there are some facts about it that you should know. Now, when they are saying that a mixture of 2-butanol enantiomers, we all know that 2-butanol is a chiral molecule. It has a chiral center. For that matter, it exhibits enantiomeric properties. So, a mixture of 2-butanol enantiomers mixed and showed a specific rotation of plus 6.76. So this means that when these two enantiomers are mixed, we are going to get a specific rotation for it, which is what? Plus 6.76. That's what you should keep in mind. That's what the question is saying. Now, you should know that the individual or the constituent enantiomers have different properties as compared to the mixture. The mixture may be having a boiling point of, let's say, 26.7 degrees Celsius, whilst their individual enantiomers may be having, let's say, 14.6 degrees Celsius. So you see, the mixture itself has a different properties as compared to the constituents of the enantiomers. So now they are saying that what is the composition of the mixture? If they are asking for composition of mixture, they are asking you that what is the composition of, let's say, R enantiomer and the composition of S enantiomer, or in the mixture. So you are going to consider the mixture as one. Okay. So given the specific rotation of pure S has a specific rotation of what? Positive 13.52, and R. So you see, also you should note that the configuration and the degree of rotation, the direction of rotation doesn't relate in any way. There can be a situation where we are having an S enantiomer, all right, but it will be rotating the plane polarized light in the positive direction, okay, or clockwise, and the otherwise too, where the R will be rotating the plane polarized light in anti-clockwise direction. Now, they are asking you to find the composition. So all what you have to do is just to list your data down. This is the specific rotation of the mixture, positive 6.76. Specific rotation of the pure S enantiomer, 13.52 degrees. Specific rotation of the R enantiomer, negative 13.52. Now, there's a relation that, if you want to find the composition of it, there's a relation which says that the specific degree or the specific rotation of the mixture of enantiomers is equal to the R component or the R enantiomer component or the R enantiomer composition. Likewise, you can also say this with the fraction. So we can represent this one as the fraction of what? The R, okay, the fraction of the R component times its specific rotation plus the fraction of the S component times its what? Specific rotation. Now, there are two variables here. So what do we have to do? We have to make one the subject. We have to manipulate it in a way that we are going to have only one variable throughout. But as we said, the mixture is one. So this means that the components of the R and the components of the S will sum up to 1. For that matter, we can make something the subject in order to get only one variable. So let's make R the subject throughout. So if you're making R the subject, then S from here is equal to 1 minus the R component. Understand? So it means that wherever we see S, we are going to put 1 minus R component. Now, this 6.76 is equal to the R component times its what? Specific rotation. So as a simple arithmetic, you can see times its specific rotation. So times its specific rotation, which is negative 13.52 R component plus, so this one is going to give you 13.52 minus negative 13.52 R component. So this one and this one will give you what? Negative 27.04 R component. And you bring this one to the other side. When you bring 13.52 to the other side and you do your normal subtraction, you are going to get 6.76. but this time around it is negative. So that we make R component the subject. R component is equal to this negative 6.76 divided by negative 27.04. So at the end of the day, it's going to give you 0.25. So this is the out of the whole mixture, it contains 0.25. Okay, which when you are converting it into percentage, it's going to be 25%. So if you are calculating for the S component or the S fraction or S composition, the S composition will be equal to 1 minus the R composition. Okay, so 1 minus the R composition is 0.25. So at the end of the day, you are going to get 0.75 or 75%. So this is how you are going to go about a question when they ask you to find the specific, or you are asked to find the composition of the enantiomer in, let's say, a mixture. Okay, so in my next video, I'll be describing how to determine the most stable sugar, and also its exceptions that you should also focus on, because in every chemistry rule there are some exceptions that you should consider. Alright, so see you in my next video, and don't forget to subscribe, like, and if possible, if you want to comment on anything, you can also comment on my video, a place where you don't understand. I'll make sure I'll make a video about it, post it to my channel, and also alert you. Thank you very much for watching my video.